Hi guys, we are on the Unit 2 Day 3 lesson, and this is the second video. We're going to start with some examples here. The first one is pretty straightforward. We just have some information about two vectors A and B. The magnitude of A is 7, the magnitude of B is 12, and it says that the angle between those two vectors is 60 degrees. So we're going to find the first question is finding A dot B. So it really is just as easy. I'm going to write out the formula just to kind of remind everybody that A dot B is magnitude of A times magnitude of B times cos theta. So this is going to be 7 times 12 times cos 60. And we get 42. So remember that the answer here is a scalar. That's the dot product is sometimes called the scalar product. So especially just for kind of general vectors here, there's no units. It's just a measurement of how much of vector B is helping vector A. So it's about, it's like showing whether it's positive or negative or zero is really the main application for kind of theoretical vectors. We will get into some applications of the dot product in some kind of physics applications later on. The next one is looking at B dot A. Now, is that going to be any different? Remember, our equation is the magnitude of the first one times the magnitude of the second one, so magnitude of B, magnitude of A, cos theta. So here we've got 12, and hopefully you guys can see 12 times 7 times cos 60. Obviously that's going to be the exact same thing. And I think that looking at these two things, we can see right away that this is two things multiplied times the cos theta. The order does not matter there. So this is going to be an indication here that the dot product is what's called commutative. So the order doesn't matter. You can swap those two numbers or the two vectors around and the result is the same. So vector A dot B equals B dot A. And that's not going to be true for all vector operations, but it is true here for the dot product. These same vectors, let's look at calculating A dot A. So can you find the dot product of a vector with itself? So this will be the magnitude of A times the magnitude of A times cos theta. So the magnitude of A is 7. The magnitude of A, again, is 7. What about cos theta? If I had like vector A there and the same vector, what angle would be between those? If we put them tail to tail, theta would equal 0 degrees. So here we don't have any visible angle if we put them tail to tail, so I'm going to have the cosine of 0. And hopefully we remember cos 0 is 1, so this is 7 times 7 times 1, so just 49. So what could we generalize about the dot product of any vector with itself? For example, V dot V would equal the magnitude of V times the magnitude of V times cos 0. that's just going to be the magnitude squared, because cos 0 is always going to be 1. Okay, so you can kind of generalize, if you have a vector dotted with itself, you just square the magnitude, and you don't have to worry about the cos of the angle because it's going to be 1. Now, we're not really dealing in these ones with the A and B anymore, but we're looking at our special basis unit vectors, I hat, j hat, and k hat. So here, I hat dot I hat is the magnitude of I hat times the magnitude of I hat times cos theta. Now we know I hat, j hat, and k hat are all unit vectors. That's going to be 1 times 1, and because it's dotted with itself, that's a cos 0. So 1 times 1 times 1 is just 1. So I hat dot I hat would be 1. What if we do j hat dot k hat? We'd have the magnitude of j hat times the magnitude of k hat times cos theta. We know again that these are unit vectors, so we've got 1 times 1. Now, what's the angle? Remember, j hat is a unit vector along the y-axis, and k hat is a vector along the x-axis, or the z-axis, pardon me. The angle between the y-axis and the z-axis we know is 90. So this is going to be cos 90. So that's 1 times 1, and the cosine of 90 is 0. So that will give us 0. And I know that's showing a lot of steps to do a pretty simple calculation, but I wanted you guys to see, especially the first time here, why that is and where that comes from. So that last example kind of brings us to something really, really important with the dot product. If we have two vectors that are perpendicular, their dot product is always 0. And it can be really handy to know if two vectors are perpendicular. There's a lot of places that that's going to come in really, really in handy and be a very important thing to be able to find out. So basically we're kind of analyzing this. If magnitude of u, magnitude of v, cos theta equals 0, we have three choices. Either magnitude of u is 0, or the magnitude of v is 0, or the angle between is 90 degrees. And that means that we would have perpendicular vectors. Remember that symbol there for perpendicular. We would have u is perpendicular to v. So this is a really important thing to be able to find out. If you know for sure that your two vectors are not 0 vectors, but their dot product is 0, then you know that they're perpendicular. So if u dot v equals 0, and we need to know that they're non-zero vectors, then that tells us that the vectors are perpendicular. And this is one of those if and only ifs. If they're perpendicular, we also know that the dot product is 0. So I'm going to want you guys to really pay attention to this. If you see anything in vectors and it says these two vectors are perpendicular, the first thing that your mind should think is dot product equals 0. The minute you hear the word perpendicular, dot product equals 0. I'm going to write that in big letters. So as soon as you hear any vectors are perpendicular, dot product is 0. That's going to be so important. If you see a dot product equaling 0, you should automatically think, assuming that they're non-zero vectors, you think right away, oh, I know that they're perpendicular. If you know that they're perpendicular, you think u dot v equals 0. That connection is going to be really, really important as we go through the next 2 units. Just to kind of summarize some other properties here of the dot product. The first one we talked about in that early example, that we have u dot v is equal to v dot u. That's called the commutative property. It is, you are able to swap the order when you're doing dot product and it doesn't change the answer. Distributive property works. So if you have a vector dot the sum of 2 other vectors, you can do u dot v plus u dot t, kind of as shown there. We also talked about this one. If you have the dot product of a vector with itself, it's just that magnitude squared. And the last one, if you have a scalar multiple of either of these will not affect it. So you could have k times vector u dotted with v. That's the same as u dotted with k times vector v. And that's the same as k times the whole dot product. So this order doesn't matter. And if you kind of wrote this one out, that this would be, either way, you're going to have a factor of k in with your dot product formula. So since it would be the k value times the magnitude of u, then times magnitude of v cos theta. Here it would be magnitude of u times k times magnitude of v. Because it's just all those elements multiplied, the order of that multiplication doesn't matter, and that scalar could get multiplied in wherever it wanted to.